This is a good moment to have a look at the main file. So in this file, you have essentially all the functions that you can run to make calculations on a given project. So one given project has identifiers, as I explained earlier, the system identifier and the instance identifier. The very first thing to do once you have written the user files and written the system name and instance name is to create a new DSA structure. So to run this complete block at once, I just do Control-Enter, and the number of lines are printed in the command window. Essentially, we see that this function has called another function called DSA set, indicating that the DSA structure has been updated. This is always the case, but what is particular to this DSA new function is that it has, before updating it, created a new DSA structure. This new DSA structure, which you can find here, has a number of fields. We will cover them all. Some fields are pre-filled. Some other fields have not been defined yet and will be defined while calling the different functions. So as you may have noticed, part of the presentation was not recorded due to a small technical problem, but let me tell you what I did in the meantime. I essentially displayed the content of DSA.data, where we can see a number of fields. We see the field F1, which is the fundamental frequency, as well as the other substructures that were defined in the data file, the base values, the parameter structure, as well as the delay structure, which is here not defined in the data file, but initialized directly by the toolbox. Then I showed the content of the parameter structure, the RLC values, the omega-1 in radians per second, as well as the value of capital Vs, which will be used when defining the inputs. I can also access the lists of variables. I find once more the large signal variables and the small signal variables, as well as additional fields which are not important for the moment. Naturally, if I want to check that the toolbox has defined all large signal states, I can also develop this particular cell. I find indeed the inductor current and the capacitor voltage. I suggest we continue with other fields of the DSA structure. There is some information that is provided, which we can check. Here we find the path to the system, the path to the instance from the DSAnalysis folder. We find capital letters and lowercase letters. In this particular case, both sets of letters are the same, but they can be different or could be different. N is the number of state variables, M the number of input variables, P the number of output variables, and D the number of delayed variables. There are also a number of functions or function handles that are defined automatically by the toolbox. I will get to that later, but essentially these functions help make the interface between the toolbox and the user-defined files, listing the variables, equations, harmonic domain data, and inputs as a function of time. A number of calculation parameters are defined by the toolbox. Naturally, at this point, there will be no time domain or harmonic domain results. So if I try to access these, we see that the structure has no fields. However, some parameters are already defined for the collocation method, the time domain simulation methods and the frequency lifting method, transformation method. We can start having a look at what is inside the call or the structure for the collocation method. Essentially, a number of entries which are detailed in the user manual. HM is the maximum harmonic rank for the calculation of the periodic trajectory. The Jacobian type is either analytical or numerical. The Jacobian reset is set to 1, and so on. We will get to this once I dive into the details of the collocation method. Let's say we would like to find the steady state values for the inductor current and the capacitor voltage when we apply certain values for the voltage source. For the collocation method, this input variable will be defined as a harmonic vector. So to understand what a harmonic vector looks like, I will rely on chapter 5 of my thesis. Harmonic vectors essentially look like this. They are a finite dimensional vector of Fourier coefficients starting from the from the Fourier coefficient related to the negative frequencies up to the Fourier coefficients related to the positive frequencies. So to define the harmonic spectrum of input variables and give initial guesses for states and delayed variables, this is something you do in the HD or harmonic domain file. There is naturally quite some information which you can read by yourself. In any case, in this particular file, you have to define the base frequency that describes that is related to the vector of Fourier coefficients that is defined next. In this function, you can also access the param structure. So you don't have to give numerical values directly. You can use the numerical values that you have defined in the data file. Let's say we would like to solve the system with just a constant voltage, let's say a DC voltage. Naturally, to define a constant voltage, we have to communicate the Fourier coefficients related to the index 0. And this is what this function can be used for. It indicates that inside this vector of Fourier coefficients, the index 0 will be equal to this to the value of this parameter. To solve the collocation method with only DC components, we set the maximum harmonic rank or the maximum harmonic index to 0. We choose the Jacobian type as numerical. This is a very simple system, so we do not need the analytical version at this point. We will define the inputs from the user-defined files, as well as the initial guess from the user-defined file. Naturally, in the user-defined file, I have not specified anything for the unknown states or unknown delays. Naturally, there are no unknown delays, so I do not have to give initial guesses. But also, if I do not specify any harmonic vectors for the states, then the toolbox automatically initializes these vectors to 0. So this is equivalent to solving the collocation formulation, but with the initial guesses set to 0. As tolerance for the algorithm, I put 1 to the minus 6, and the LDISP is essentially the number of points per fundamental period for the resampling of the waveforms that results from the collocation method. To run everything there at once, I do Control-Enter. And again, a number of lines are printed in the command window, and a number of plots are displayed. Starting from the end, I see that one of the plots gives the absolute residual error from the collocation method, I see that there are two unknowns, one here and one there. This is normal because we are solving for one constant value, so one index 0 Fourier coefficients for two states. So this is indeed two unknowns, and that the error is maximum 10 to the minus 14. So this is already a first proof that the collocation method has found a solution with a very small error. Additionally, for non-delayed systems, the eigenvalues of the Jacobian give information about stability. We see that we have two eigenvalues, which makes sense because we have two states, each of them being described by only one Fourier coefficient or one sample point in the collocation method with a negative real part. So we know that the operating point that has been found by the collocation method is stable. Let's go to the printed lines. First, we see that the DSA set has been automatically called by the DSA run collocation method function. So if any parameters had been modified, then the toolbox uses the latest version of the numerical values. Then we see some initialization, which is essentially the toolbox calling the HD file to retrieve the harmonic spectra, and then information related to the solver that has started. I am working with the Levenberg-Marquardt solver provided by the fsolve function. Then we see a number of iteration loops where we can check the evolution of the residual in particular. We see that it has reached a very, very small value. Finally, we see that the equation has been solved. There is also some information related to the elapsed time and that the solver is done. Furthermore, we see that the results have been extracted and that since there are no delays, then the Jacobian eigenvalues are indeed the Floquet exponents, which I showed you just before. I would like to see or visualize the results of the collocation methods. So there are essentially two ways of doing that. The first way is to access the results thanks to the DSA toolbox. We recall that the results are stored in the time domain, TD structure, and the harmonic domain, HD structure. So if I access, for instance, the harmonic domain structure, I see that now I have one substructure, which is identified like this. HD tells me that I'm looking at harmonic data. Call that this particular structure comes from the collocation method and that it covers data for 1p. 1p is one fundamental period. If I look inside this structure, then I find the value of all the variables. Indeed, the source voltage was set to 1 or 1 volt, unless I'm working in per unit, in which case it would be 1 per unit. And then I have the results for the inductor current and the capacitor voltage. Essentially, this makes sense since in steady state, if we set 1 volt here, the current in steady state will become 0 and the voltage across the capacitor will be equal to the voltage at the source. I have also other values. F is a vector with all the frequencies. Here is just 1 time 0 Hertz. HM is the maximum harmonic rank, which we define to be 0. And HM is the number of Fourier coefficients. We have only one, which is the one related to 0. And then the fundamental frequency, which is again 1 Hertz.